We now begin our discussion of acid-base equilibria. We'll start off with a review on the Arrhenius classification of acids and bases, remembering what we learned back in General Chemistry 1. Then we're going to move to a broader classification, the Bronsted-Lowry acid-base definition. We'll look at the pH scale in water and autoionization, and we'll finish up with strong acid and base calculations for aqueous solutions. In our next video, then, we'll look at weak acids and bases, more complex equilibrium, and finish up with the most broad of the classifications that we will look at, the Lewis acid-base definition. Acids and bases are ubiquitous. They're extremely important. They're in your body, they're in the air, they're all around you. And here are just a few common examples, household items that you've come across that you've handled that are acids and bases. In general, acids are sour substances, bases are bitter substances. And not that you want to taste any of these or some of these, but these are common things that you've come across that are acidic and basic. Back in Gen Chem 1, we had a definition for acids and bases, the Arrhenius classification. Looking at substances in water, we identified acids as proton donors. Those are things that would dissolve in water to release a proton. And we can show this one of two ways. The first way is the way I will more commonly do this in lecture. The second way is the way your book and many places handle this. You can write weak acid or acid, strong acid, going to proton plus the anion, or you can write the strong or weak acid reacting with water to go to hydronium ion plus A minus. So H3O is identified as the hydronium ion. I'll equivalently use proton and hydronium ion equivalently bouncing back and forth, so please be comfortable with both of those terms. And then a base is a substance that releases hydroxide in the Arrhenius classification. So if we have an acid and a base react, the hydronium ion and the hydroxide ion will react, and then the counterions will make the salt. So this is an Arrhenius acid-base reaction. The Bronsted-Lowry classification is a broader classification encompassing compounds that are not necessarily hydroxide donors, but still show basic behavior. So the Bronsted-Lowry acid-base definition is based on proton transfer, both from the acid and base side. An acid is a proton donor, anything that releases a proton, so an acid must contain hydrogen in its formula. And then a base is a proton acceptor, any species that accepts a hydrogen ion. A base has to contain a lone pair of electrons that will bond to the proton. And an acid-base reaction is a proton transfer process. So we can see that the Arrhenius acid is the same as the Bronsted-Lowry acid, but the Arrhenius base is only a small subset of all possible Bronsted-Lowry bases. Here we can see this in reaction form. Hydrogen chloride in reaction A is our acid. When this goes into water, the small blue ball there will come off the hydrogen chloride and stick onto the oxygen lone pair, producing the hydronium ion and chloride ion. In reaction B, we have ammonia, which is not a Arrhenius base, but is a Bronsted-Lowry base. In water, ammonia can abstract a proton from water to form the ammonium ion and hydroxide ion. Now in these two reactions, we can see that water is acting as a base in one instance and as an acid in another instance. So water is what we call an amphiprotic system or amphiphilic system. It can act as either a base and accept a proton, or as an acid and donate a proton, depending on the conditions. Next, we're going to look at conjugate acid-base pairs. Here we have a reaction written down, H2S, that's in water, that's hydrosulfuric acid, with ammonia, producing the monohydrogen sulfide anion plus ammonium ion. So we notice that sulfur on one side is H2S, and on the other side it's HS minus. This represents what we call a conjugate acid-base pair. The core of the system, the sulfur, stays the same, but we simply change the number of protons, so protons shuttle off or onto the system. So the hydrosulfuric acid is the acid side, and the monohydrogen sulfide anion is the base. Likewise, ammonia and ammonium constitute a conjugate base-acid pair system, ammonia being the base and ammonium being the conjugate acid. In the Ford reaction, ammonia accepts a proton to form ammonium. Hydrosulfuric acid donates a proton to form hydrogen sulfide anion. In the reverse reaction, ammonium donates a proton to form ammonia, and monohydrogen sulfide anion accepts a proton to form the hydrosulfuric acid. So we can see H2S and HS minus are a conjugate acid-base pair. The conjugate base in general has one fewer proton and one more negative charge than the acid. And then ammonia and ammonium are a conjugate acid-base pair as well. The conjugate acid has one more proton and one fewer negative charge than does the base. A Bronsted-Lowry acid-base reaction occurs when an acid and a base react to form their conjugate base and conjugate acid, respectively. It's a proton transfer process. So here we see acid 1 converts to base 1, and then base 2 converts to its conjugate acid 2. Here's a series of acid-base reactions, and we can identify the conjugate acid-base pairs in each. So, in the first reaction, hydrogen fluoride reacts with water to produce fluoride and hydronium ion. HF and F minus are a conjugate acid-base pair, and H2O and H3O plus are a conjugate acid-base pair as well. Reaction 2 is formic acid reacting with cyanide to form formate and hydrogen cyanide. Cyanide and hydrogen cyanide form a conjugate acid-base pair, as do formic acid and formate. You can do this for all 6 reactions. One thing to point out here is that some molecules, like water, can act as a base or an acid depending on what it's interacting with. So water acts as a base in reacting with hydrofluoric acid, but it reacts as an acid in reaction 4 when reacting with monohydrogen phosphate dianion. We can also see that monohydrogen diphosphate anion, monohydrogen phosphate dianion in reaction 4 is a base, and monohydrogen phosphate dianion in reaction 6 is an acid. So it depends on what species you're interacting with. Now, the net direction of an acid-base reaction depends on the relative strengths of the acids and the bases that are involved. A reaction favors the formation of a weaker acid and weaker base. The stronger acid will convert to its weaker conjugate base form, and the stronger base will convert to its conjugate weaker acid form. And so we can see here with a dihydrosulfuric acid plus ammonia reaction, the reaction tends to go in the forward direction, from the stronger acid and base to the weaker acid and base. This reaction favors the formation of products. Here's a chart that shows the relative acid strengths and the relative base strengths of a series of compounds. You don't need to memorize this chart. This chart is something that is worth looking at in terms of conjugate acid-base strength. Later on, we're going to come across a simple factor that allows us to identify what the strongest acid and what the strongest base is, which direction the reaction proceeds, and so forth when we get to acid dissociation constants. But for now, let's just notice that, for example, the top acid is hydrochloric acid. Its conjugate base is chloride, which is negligibly strong as a base. So chloride is not a base in water. Towards the bottom, you can see, for example, sulfide anion S2 minus is a strong base, whereas HS minus monohydrogen sulfide anion is an insignificantly strong acid. Now, as we look at this, it's important to remember that we're working in an aqueous solution with water. And water has an unusual property in that it dissociates very slightly into ions by reacting with itself. This is sometimes called self-ionization or autoionization. So the reaction is as follows. Two water molecules react to produce the hydronium ion and the hydroxide ion. And you can see that, with the space-filling model shown below, the proton comes from one molecule onto the lone pair, oxygen on the other molecule. We can look at the equilibrium expression for this, and that's shown here. This is a very important reaction. You should remember this equilibrium constant. So two molecules of water will produce the hydronium ion and the hydroxide ion. The equilibrium constant is shown here. Of course, remember, water is a liquid. Its mole fraction is approximately 1, and so we put 1 into the expression such that the equilibrium constant becomes equal to the proton concentration times the hydroxide concentration in water. And this is given a special letter. It's called K sub W. And that is 1.0 times 10 to the minus 14 at 25 degrees Celsius. You should remember that. This is something you will use throughout this semester and in the future as well. So in pure water, then, we find out that since the stoichiometry is 1-to-1, the hydronium or proton concentration is equal to the hydroxide concentration. And since those two are equal and the product is equal to 1 times 10 to the minus 14, they're both equal to the square root of 1 times 10 to the minus 14, or 1.0 times 10 to the minus 7. Both ions are present in all aqueous solutions, such that in any situation, the hydronium concentration is Kw divided by hydroxide concentration, or simply rearranging, the hydroxide concentration is Kw divided by the hydronium concentration. That is an important relationship which you should remember. Now, how does Le Chatelier work here? Well, we see that in reaction A, if we increase the acid concentration, that will increase H3O plus on the product side. Therefore, the hydroxide concentration will need to decrease because the product has to be constant. And correspondingly, in reaction B, if we decrease the acid concentration, the hydroxide concentration will necessarily increase. So, higher hydronium, lower hydroxide. Higher hydroxide, lower hydronium. And if we add acid, we see what happens. Likewise, if we add base, we see what happens. The hydronium hydroxide concentration product is constant. If one goes up, the other goes down. Now, we often use the phrase acidic and basic to indicate the relative concentrations of hydronium and hydroxide ions. Since we know the neutral situation has 10 to the minus 7, in an acid solution, the hydronium ion concentration is greater than hydroxide, and hydronium will be greater than 10 to the minus 7. In a neutral solution, they're equal, and in a basic solution, the hydroxide will become greater than 10 to the minus 7. So we can see here, this is the relationship. We can always calculate what these values are using our Kw relationship that we know now. Now we have something we call a pH scale, and we have a definition, which is with the 3 stars here. You can tell this is one that you need to remember. The pH is equal to minus the log of the hydronium ion concentration, or minus the log of the hydrogen ion concentration. Now, just a small note that's not important for this class, but is to give us a strictly more accurate value. pH is actually minus the log of the activity of the hydrogen ion concentration. And the activity is something we learned about back in our previous equilibrium chapter. If you remember the Van't Hoff factor, little I, that is something that can be used as a correction, or it's related to the correction that we use. But we won't do it in this class. But in the future, you may use that correction for more precise measurements. So the pH of a solution indicates its relative acidity. If the pH is less than 7, it's an acid solution. If it's 7, you have a neutral solution. And if it's greater than 7, it's a basic solution. Here are a series of common materials, and the pH is associated with those materials. Higher pH, lower hydronium concentration, less acid solution. Lower pH, higher hydronium, more acid. Now we can see an important relationship between hydroxide, hydronium, and Kw using our logarithmic relationships. We know that pH is minus the log of the hydrogen ion concentration. Now we can go back to Kw, which is equal to the product of hydronium times hydroxide, and that happens to be equal to 10 to the minus 14. If we know that the pH is minus the log of the hydronium concentration, we can also define the pOH as minus the log of the hydroxide concentration. And then pKw is minus the log of Kw. So that if we take logs of both sides of the upper equation here, we end up with the following relationship. pKw, which is equal to 14, is equal to pH plus pOH. Since Kw is a constant, pH, pOH, hydronium, and hydroxide are always interrelated, such that when hydroxide goes down, that tells us hydronium is going up, or if hydronium goes down, hydroxide goes up. If pH goes down, pOH goes up. If pOH goes down, pH goes up. And this is a simple chart that shows us all of the pH values from -1 up to 15, showing the values that we see for hydroxide, hydronium, and pOH as well. Strong acids completely dissociate into ions in water. So we know that a strong acid will go into water to form hydronium and A-. So strong acids are strong electrolytes. Dilute solutions of strong acid contain no HA molecules. Now I've written on here approximately because that is strictly correct. Your textbook does not say approximately, but it turns out that there are traces of the strong acid molecules in water, but the level that they're present is far below the precision of the measurements or calculations that we'll do in this class. So I've written down approximately just to let you know that that is strictly correct, but your textbook does not use that. If all the strong acid molecules have been converted into products, so we can say that the hydronium concentration will equal the anion concentration, the conjugate base, which is infinitely weak, close to it, and that's approximately equal to the acid concentration that was delivered to the solution. Since hydronium and A- are large and HA is approximately 0, the equilibrium constant then becomes very large. It's much, much larger than 1. So the extent of dissociation is shown here. The reaction is shown, the before reaction is shown on the left-hand box, the green box, And then after dissociation, the HA goes to very close to zero, and hydronium and A- become equal and large. And so there are approximately no HA molecules in solution. The strong acids were ones that we learned back in Chapter 4 of General Chemistry 1. The hydrohalic acids, hydrogen chloride in water, hydrochloric acid, hydrogen bromide in water, hydrobromic acid, and then hydrogen iodide, which in water is hydroiodic acid. Those are all strong acids. And then the oxo acids, where the number of oxygen atoms exceeds the number of ionizable protons by 2 or more. And the common ones are nitric, sulfuric, and perchloric. Chloric is also a strong acid, but it is not a common acid because the chlorate ion is not particularly stable. The strong bases that we learned earlier with the group 1 and lower group 2 metal hydroxides, it turns out that the group 1 and lower group 2 metal oxides are also strong bases. Now, calculating pH for strong acids and strong bases is quite straightforward. We can use our earlier definitions and relations along with the understanding that the molecule completely dissociates. So for a strong acid, the HA that we deliver to solution is equal to the hydronium ion concentration, so that pH equals minus the log of the hydronium equals minus the log of HA that we delivered to solution. For group 1 metal strong bases, then the metal hydroxide you deliver in solution is the hydroxide that will be in solution, so POH is minus the log of the OH. For group 2 strong bases, we need to add a factor of 2 in because there are 2 hydroxides for each metal. So POH is minus the log of 2 times the metal hydroxide concentration you delivered into solution. Weak acids do not dissociate completely. They only dissociate slightly to form ions in water. In a dilute solution of a weak acid, most of the HA molecules are undissociated. We do know that the hydronium ion and the conjugate base concentrations are equal because of the 1-to-1 stoichiometry relationship, but they're much less than the initial weak acid delivered to solution. Here's our weak base relationship. Hydronium times A- divided by HA times water, and it typically has a very small value, usually on the order of 10 to the minus 2 or less. The extent of dissociation for weak acids is small. So here's our weak acid before dissociation, and then after it goes into water, we get a little bit of hydronium and a little bit of its conjugate base. Most of the HA molecules are undissociated. And this can be illustrated with a reaction from back in Chapter 4. We know that zinc is a metal that reacts with acid by displacement, and it'll react differently with a strong acid and a weak acid. When zinc reacts with an acid, it produces zinc ion and hydrogen gas. And you can see on the left-hand side with 1 molar HCl, you get copious bubbling because the concentration of protons is very high. On the right-hand side, you can see very few bubbles because the weak acid, 1 molar acetic acid, has less protons. This is a kinetic effect. Zinc reacts rapidly with the strong acid since the hydronium concentration is much higher in the strong acid. Now let's look at the acid dissociation constant. The way we write the equilibrium constant out for a weak acid, we don't include the water because its mole fraction is approximately 1. So the acid dissociation constant for a weak acid is given by the product of the hydronium ion concentration times the conjugate base concentration divided by the weak acid concentration. And just as we have pKW, pKW, pH, and pOH, We also have a pKa, which is minus the log of the Ka. The value of Ka measures the strength of the acid. Stronger acids have higher hydronium ion concentrations and larger Kas and smaller pKas. Weaker acids have lower hydronium concentrations, smaller Kas, and larger pKas. Here we can see the effect of the Ka on the percent dissociation for a series of weak acids. These all have the same initial concentration. They're 1 molar weak acid. If the acid dissociation constant Ka is relatively on the higher end, on the order of 10 to the minus 2, we see that typically you'll have for a 1 molar solution around 10% dissociated. If we go to a moderate Ka, with 10 to the minus 5 being a typical value, the dissociation drops down to 0.3%. And for low Ka values, this can become 1 part in 10 to the 5th. When we learn about strong acids, there are really 6 common strong acids. If you're not dealing with one of those and it's a common compound that is acidic, it's a weak acid. But your book has classified 4 of the common types of weak acids as following. HF as being one. Along with HF, you could have acids where hydrogen's not bonded to oxygen, like hydrosulfuric acid or hydroselenic acid or hydrotelluric acid or hydrogen cyanide or carbonic acid. And then we have oxoacids when the number of oxygen atoms equals or exceeds by 1 the number of ionizable protons, such as hypochlorous acid, chlorous acid, nitrous acid, phosphorus acid, any of the OUS acids, and organic carboxylic acids of the general form RCOOH, such as acetic acid. There are many other types of weak acids, but these are the common ones that you will encounter in our course, and subsequently, these are the most common ones you will encounter in the future. Here we have an acid dissociation constant table for some common weak acids. This is a very small subset. Your book has a much larger table available to you. There are entire compilations of these because there are many thousands of known weak acids. We'll continue on with more complex systems in our next video.